Uh, Hello, everyone. So let us actually continue our discussion. This is going to be part four of this of these lectures on signal integrity. And now we are actually going to be talking about the next important reasons for signal integrity issues, which is the crosstalk. So, as the name suggests, crosstalk mainly deals with how one link, called as the aggressor, affects an adjacent link, called as the victim. So for example, consider this setup here, where this could be either the PCB or on a single package, where there are multiple links which are placed next to each other. And let us look at how the presence of two links, called as the aggressor links, next to the victim link, affects the signal performance in the victim. So what can happen is, imagine the signal is sent from the transmitter on this aggressor. And what happens is, because of the parasitic capacitance between the links, as well as the parasitic inductance between the links, some amount of the signal essentially couples from this link onto the victim link. And similarly, you can also have signals coupling from this link also onto the victim link. So, this effect of signals coupling from one link to the other, because of these parasitic capacitance and inductances between the link, is often called as crosstalk. And when you talk about why is crosstalk an issue? Crosstalk is an issue because this kind of sort of signal crossing from one link to the other often results in noise as well as oscillations in the signal on the victim. And this can, as we know, such oscillations can lead to signal quality issues. For example, it can close the eye, and therefore it can lead to bit errors. It can lead to timing issues, and so on. And in this particular discussion, we are also going to talk about two different types of crosstalk. One is called as a near end crosstalk and a far end crosstalk. So the definitions of near end and far end crosstalk really depend on where we are looking at the crosstalk signal versus the input. So for example, far end crosstalk is defined as how much noise power, crosstalk power, is coupled into the receiver for an input power that is transmitted from the transmitter here. And because the receiver and transmitter here are located on opposite ends of the links, this is called as far end crosstalk. Near end crosstalk basically refers to the same kind of crosstalk, but it happens in the near end where the transmitter and receiver are actually on the same side versus on opposite sides as in the far end. So that is the far end crosstalk and near end crosstalk. And we will also talk about how to actually mathematically describe this next and fixed, as they call it. So here, far end crosstalk. So imagine you are sending basically a power. This is the incident power through the aggressor one, and let's say that is PA1. And we are, of course, talking about the real power here, which is the real part of the complex power. And similarly, there's a power PA2 that is sent through the aggressor 2 from the transmitter. And so we are going to now decouple these. So we are going to talk about the effect of each link individually. So the power that is the log to the base, 10 times log to the base 10 of the power that is received at the receiver due to aggressor 1 over PA1 is defined as the near end crosstalk. Is defined as a far end crosstalk. And similarly, the 10 log to the base 10 of the power received at the receiver over the power that was sent through the second aggressor is defined as a near end crosstalk, which is basically what I discussed in the previous slide. So now let us talk about how this crosstalk process actually happens. As I mentioned, there are two different types of crosstalk. It can happen because of capacitive coupling, or it can happen because of inductive coupling. So let's look at how it would happen in terms of capacitive coupling. So imagine you had, for simplicity, we're going to consider mainly microstrips, but this is applicable for any kind of waveguide or transmission line that you have. It's true for coplanar waveguides, it's true for strip line waveguides, and so on. But let's talk about a microstrip waveguide as shown here. So here you have basically a common ground plane for both the signal lines. And then you have this signal line 1 that's behaving as the aggressor, and you have signal line 2, which is behaving as the victim. And obviously, because the conductors have a certain height, there is definitely going to be some capacitance between basically the thickness face on this side and the thickness face on this side, of the two signal lines. And therefore, there's going to be some parasitic capacitance per unit length that's going to be present along the length of this link. And so now imagine what happens if, say, a signal transition occurs on the aggressor. Now, remember the property of a capacitor. What is the main property of a capacitor? So the main property of a capacitor is that the capacitor does not like voltage changes across itself. So think of a capacitor as an inertia for voltage change, right? So if you had a capacitor which has two terminals and a one terminal of the capacitor is suddenly changing in voltage, because the capacitor doesn't like the voltage across it to change, the voltage at this terminal will also increase by a certain amount, so that the differential voltage across the capacitor is minimized, right? So that is the reason why one node being pulled up basically capacitively causes the other node also to be pulled up, because differential voltage still has to be minimized because the capacitor has inertia. So, how this works in practice is, so here, imagine that you had on the aggressor, you had a signal that is transitioning from 0 to 1, as shown here. So when the signal suddenly goes from 0 to 1, as I mentioned earlier, imagine that the victim was originally at 1. So because the aggressor is going from 0 to 1, the victim is now going to overshoot from the value 1 up a little bit. And then after some time, it's going to come back to the original value, because remember, the victim is still connected to some source, and the source is going to pull it back to the original value that the source wants it to be, right? So it's gonna. So what's gonna happen is, if the victim was originally at 1, it's gonna overshoot a little bit, and then it takes some time for it to come back. And the time that it comes back really depends on the time constants of the interconnect. For example, of this link, because for example, if it has some parasitic, it has some capacitance, then it's basically something like the RC time constant for the discharge or charging, right? So what happens if there's a 0 to 1 transition on the aggressor, but now the victim was originally at 0? Now the 0 signal suddenly going to go up, and then it's going to go back to 0. And similarly, you have the reverse case when the aggressor goes from 1 to 0 now. If the victim was originally at 1, it is going to be pulled down a little bit. The voltage is going to go down, and then it is going to charge back up again to 1. And similarly, you have the same case you have when the signal at the victim was 0 and the aggressor was going from 1 to 0, then the signal is going to be pulled down below 0 a little bit, and then it's going to go back to 0. So when I mean 1 and 0 here, they actually refers to bit values, but they correspond to physical voltages. So what I'm really talking about here is the voltages kind of going up and down. So what happens is, imagine a digital signal is now traveling across the aggressor. This digital signal is going to have a whole bunch of 0 to 1 and 1 to 0 transitions. And these transitions are going to now induce constant voltage fluctuations on the victim, and hence it induces voltage noise on the victim side. And why are these particular issues? Sometimes overshoot can sometimes basically, imagine now the original bit value was 0. Now imagine there's a sudden overshoot because the aggressor was transitioning from 0 to 1. Then sometimes what happens, if the data was sampled during this time where there was an overshoot, a 0 can be now flipped to a 1, and you have vice versa in the reverse case, right? So therefore, you now end up having bit errors because of the presence of signal switching on the aggressor. And this effect is also going to be highly frequency dependent. And the reason why it is highly frequency dependent is because the coupling capacitance between the aggressor and victim is also frequency dependent. For example, if you look at a typical microstrip, which is as shown here, you see that the microstrip basically has the aggressor and victim here, and the capacitance is basically going to be a parallel combination of the capacitance in air and the capacitance in the dielectric material. But this can be considered as two capacitors in parallel. And what happens is, as the frequency increases, more and more electric field gets confined in the material, which has a higher dielectric constant because it has a lower value of capacitance. And hence, now what happens is the net capacitance, the parallel combination of both the capacitors, is now actually going to kind of go up with frequency. And because the capacitance between the aggressor and victim is going up with frequency, you find that the high frequency components of the digital signal is going to couple more to the victim. So that's why the victim to aggressor coupling is also going to be frequency dependent. And typically, high frequency noise tends to couple much more from the aggressor to the victim. And that's basically what I talked about here. And this phenomena can actually get quite complicated. For example, imagine now you can also represent this in a general way by defining something called as a capacitance matrix. Because remember, when you consider an actual sort of interconnect system, like on a PCB, a package, or even on a chip, you have a whole bunch of conductors that are present in a cross section, separated by some dielectric, where each conductor could be at a different voltage, could be transitioning, and hence you can often define something called as a capacitance matrix that describes the various capacitances between the various interconnects. So remember, Q is CV. So the charge on a capacitor is the C times V, and therefore, if you write the voltage as basically as a vector, a voltage vector, with V1, V2 up to Vn being the voltages on the n different conductors, and Q1, Q2, Q3 up to Qn as the charges on each one of these n conductors, then the charge vector is related to the voltage vector by the capacitance matrix. And the elements of this if you look at the capacitance matrix, and you can think about this for yourself, it has to be a symmetric matrix because C12, the capacitance between conductor 1 and 2, must be the same as the capacitance between 2 and 1 because it should be reciprocal. And similarly, the value C11, C22, C33, and so on refer to the self-capacitance of the conductor itself. And so the charge on any one capacitor is going to depend basically on the voltage on that, the charge on any one conductor or any one signal line is going to depend on the voltage on that line times its self-capacitance, plus the effect of the voltages on the other signal lines because of these mutual capacitance between the conductor we're talking about and the remaining conductors. So that's how you can represent this. So you can see how in a multi-signal network, you have to actually consider what are the various mutual capacitances, and then you need to consider what are the signal transitions occurring, what is the amount of coupling from the different aggressors to the victims, and then you need to kind of design your network or design your links so that you can minimize this cross coupling. So, what is one way you can think of to minimize the cross coupling? One simple way would just be to increase the distance between the conductors. Because if you increase the distance between the conductors, because the capacitance is going to be epsilon A over D, you are basically increasing D, and therefore the capacitance is going to go down, and the cross coupling is going to go down. Another method would be to use basically a dielectric material with a low dielectric constant, and that is a way to reduce this kind of cross coupling capacitance. And that is also the reason why, if you, for example, go for high-speed chips, you see that the oxide is typically made of something like TEOS, which is actually a type of oxide that has a lower dielectric constant, right? And also, another way would also not to have too many metal interconnects kind of talking to each other. So generally, if you go to a PCB, what you usually do is you have basically layers of conductors separated by a ground and voltage plane. And as we will see in a couple of slides later, is those voltage planes actually kind of shield the interconnects from one level to the other. So the interconnects on one level do not affect the interconnects on the second level, and so on. So that's another way we can actually reduce this cross coupling, right? Now, I haven't really included in the slide about inductive cross coupling because I wanted you to kind of figure this out for yourself because inductance is a very similar phenomenon to capacitance, except it happens with currents instead of voltages. So you can think of what inductive coupling would look like. So it would be the same as a capacitor coupling, but now what happens is there's a mutual inductance between one signal line and the other signal line. And why does the mutual inductance happens? It happens because the current that essentially flows through one signal line is going. So imagine there are two signal lines running parallel to each other. So the current in one signal line is going to induce a magnetic field, and that magnetic field is going to cut through the other signal line. And so when the signal line suddenly transitions, this magnetic field that's cutting through the second line, which is the victim, also suddenly changes. And the sudden change in the magnetic field cutting through the victim is now going to cause as you know, through Faraday's law of induction, is going to induce essentially a kind of voltage in this conductor, and that voltage is going to cause its own current. So what happens is now the current that is changing in this conductor because of the signal transition is now inducing a kind of a voltage noise and a current noise in the second conductor, And the amount of that induction between one conductor to the other depends on the mutual inductance between the two conductors, which again is going to depend on how close the conductors are placed to each other, right? The magnetic property doesn't really matter because generally, you don't want to put magnetic materials around these conductors, and it's going to be just mu naught. But depending on how close the conductors are, as well as the frequency, this mutual inductance can be quite significant and has to be considered when designing these interconnects for signal integrity. So as I mentioned earlier, this is a chart that shows typically how these interconnects on the PCB are fabricated. And you see, if you notice, right, on a typical PCB, have you ever wondered why, when there are two interconnects, one on top of each other, one is routed horizontally while the other is routed vertically? So they're kind of like a grid-like structure, right? As shown here, this is routed vertically, sort of into the plane, and this is routed horizontally across the plane, right? The reason they do this is because by sandwiching them in this way, or by basic, and this is called Manhattan routing, and by using this kind of Manhattan routing, what happens is you're reducing the effective overlap between the two layers of conductors, and that in turn reduces the parasitic capacitance between the conductors. Because remember, capacitance is proportional to the area of overlap. So by using this kind of Manhattan routing between two conductors placed in the sort of the same region of dielectric, as well as separating one layer of conductors from the other layer of conductors by using these VDD planes, which is the power plane or the ground plane, as well as separating the distance between the conductors as much as possible and using a lower dielectric constant, it is possible to reduce this cross coupling as much as possible to improve the signal integrity of the overall communication links. And the voltage and ground plane basically behave as a shielding layer, and they basically shield the electromagnetic field from one layer to the other layer. So the layers are now separated from each other. So these are the various ways to mitigate or reduce the amount of cross coupling. Now let us talk about the next phenomena that causes signal integrity issues, which is the frequency-dependent attenuation as well as the frequency-dependent time of flight. Now, this I'm not going to go much into detail on in this lecture because I've already discussed this significantly in the lecture on waveguides. But I will go over a little bit of it to give you a recap of how this phenomenon actually happens. So remember, whenever you have a waveguide, for example, imagine you had a microstrip or a strip line or any kind of waveguide structure, it's going to have some cross section, and and in the z direction or propagation direction, it's not going to have any variation in the geometry or the structure, right? So how would you? So you know already by solving the Maxwell's equations in such a structure, you get the electric and magnetic field to be equal to some electric and magnetic field distribution along the cross section of the waveguide times certain exponential factors, where the first exponential factor basically tells you how the signal is attenuating along the length as it propagates. The second factor tells you how the phase of the signal is changing as it propagates along the z direction. And the third exponential factor is the time harmonic dependence. That is the harmonic dependence on time. And any signal that propagates on this link is going to be basically a superposition of these various Fourier components added with certain amplitudes to get any kind of electromagnetic signal that can propagate in this waveguide structure. And these two-dimensional solutions, so the electric field along the cross section, E of xy and H of xy, also satisfy something called as a Helmholtz equation, which is given like this. And if you remember, when you solve the Helmholtz equation in the cross section, the boundary conditions in the cross sectional area, such as the fact that the electric field has to go to zero inside a metal, the fact that across a dielectric, certain conditions exist for how the normal component of the fields and the tangential component of fields must behave at the interface. These kind of boundary conditions, we know, forces only certain values, a certain kind of field distributions are possible in these cross sections. And as we know, those field distributions correspond to a certain value of k, which denotes which mode it is. And from this k, which denotes the kind of mode and the kind of field distribution in the cross section, it is possible to calculate using the dispersion relation for a given beta and a given omega what the effective dielectric constant of that basically of the material cross section is for that given mode that is propagating to the waveguide. So because, for example, if you consider in this case, I've shown you what typically how the mode would look like in a coplanar waveguide. There would be, for example, an even mode or an odd mode. So the even mode is a mode that if you take basically a cross section through the center of the waveguide, like here, and you reflect it, it's basically in the case of an even mode, you'll find that it's symmetric. It has reflection symmetry above the central axis. But in the odd mode, it'll have basically an anti-reflection. That is, whatever field distribution is here, it'll be the opposite over here. So you can have an even mode and odd mode are two possible field configurations in this cross section. And as you notice here, the field configurations are very different electric field profiles in the cross section. And so each one of these modes will end up having a very different effective dielectric constant in this waveguide. And now, because they have a different effective dielectric waveguide, because they have an effective dielectric constant in this cross section, depending on the mode, each mode will have a different time of flight. Each mode will have a different phase velocity, which is given by c over square root of epsilon effective. So imagine now you are sending a signal, and the signal is a digital signal. It's going to have multiple frequency components. And imagine now each one of those frequency components is now going to have, just dependent on its frequency, it can either excite different modes, or even in the same mode configuration, it can have a different field distribution in the cross section depending on the frequency. And hence, each one of these frequency components is going to end up having a different phase velocity as it propagates through this waveguide or through this transmission line. And therefore, they're going to arrive at different times at the receiver. And thus, if you now combine all the frequency components together to recover the signal is obviously going to have distortions because you have now changed the phase of arrival of, you have essentially created phase shifts between the different frequency components of the signal. And that is also shown here as to why that physically happens. So, for example, why would that happen in the microstrip? So, for example, here I've considered a microstrip and I've shown three different frequencies: omega 1, omega 1, omega 2, and omega 3. And in going from omega 1 to omega 2 to omega 3, the frequency is actually reducing. So omega 3 has the least frequency and omega 1 has the highest frequency. And if you actually do and obviously this is one mode, this is actually called the TEM mode. But even for a single mode, you see that as the frequency changes, the field distribution in the cross section is changing. And so at a higher frequency, more of the electric field is confined within the medium of higher dielectric constant, because it has a much higher capacitance. And as you see that as you reduce the frequency, the field distribution is getting more uniformly distributed between the medium of dielectric constant epsilon and epsilon naught. So now what is going to happen is the higher frequency will basically end up having a higher effective dielectric constant, and the lower frequency will end up having a much lower effective dielectric constant, somewhere between epsilon naught and epsilon. So what ends up happening is, if you are sending this digital signal now, it's going to have various frequency components. The high frequency components, which are going to have a higher epsilon effective, are now going to propagate much slower as compared to the lower frequency components, which are going to propagate comparatively faster, right? And because of these different time of flights, now at the receiver side, you're going to have signal distortions. And this is further continuing on what was discussed in the lecture 1 on waveguides, is that any waveguide has this kind of dispersion relation, which basically talks about the various possible mode configurations in the waveguide cross section. And also each waveguide, each mode pattern itself in the waveguide cross section can have a different if you plot the dispersion relation, can have a different curve depending on the frequency. So for example, each one of these curves represents a single mode, and you can see how the slope of the curve, which is basically related to the wave velocity, is kind of changing with the frequency, right? So, for example, what is happening here is as the frequency is increasing, you see that the slope, which was originally very large, is now reducing. And the reciprocal of the slope is the wave velocity. So initially, the wave was actually kind of faster. And then as the frequency was increasing, the wave is actually getting slower. And this basically comes directly from the dispersion relation, because if you look at the formula for the dispersion relation, you notice that it is a hyperbolic equation. So for a given k, which denotes a given mode, this is essentially the equation of a hyperbola. And therefore, for each k value, which corresponds to each mode, you essentially get this hyperbola that denotes a relation between omega and beta, called as the dispersion relation. And this is the same thing I talked about. imagine not only is the time of flight going to vary for different frequencies within a single mode pattern, but also you're going to see that as the frequency increases, sometimes you end up exciting more than one mode in the waveguide, right? So, for example, here, imagine this is the dispersion relation, which corresponds to three different modes. Then at a frequency omega 1, you can only excite one mode because it corresponds to only the curve k1. But at the frequency omega 2, you can actually excite two different modes corresponding to wave numbers k1 and k2. And therefore, because each mode pattern has a different field configuration, the signal omega 2 is now going to behave very differently compared to the signal omega 1 because it's going to have a very different time of flight. And also, it's also going to change the matching configurations and all we had talked about in impedance matching. So this frequency change is going to cause a lot of issues to signal integrity. In general, when you design a waveguide, you always want the transmitter to excite only the fundamental mode of the waveguide because it's very difficult when it excites higher order modes because it's very difficult to match your transmission line for all different mode configurations because you typically match it for the fundamental mode. So if you end up exciting higher order modes, it's going to create much more reflections and more issues in signal integrity. So when you design your waveguide, you always want to end up designing the waveguide so that it can only, up to the frequency range of operation, it only ends up exciting the fundamental mode, typically the TEM mode. And yeah, and so this is basically what I talked about, like, and this is representing it more pictorially, so you get a better understanding of it. So the transmitter side, you have a digital signal, as we talked about, it's going to be a very broadband signal composed of several frequency components. And each one of these frequency components is now going to have a different time of flight because it's going to probably excite a different mode, or even if it excites the same mode, within the same mode itself, the field configuration is going to change in the cross section of frequency. And therefore, each one of these frequency components is going to end up having a different velocity along the waveguide. And therefore, they're going to arrive at different times. And that's when you superimpose all these signals, it's going to lead to signal distortion. And the signal distortions, as you know, can lead to bit errors, timing issues, and so on. So on top of this frequency dependent behavior of the signal propagation, the link, basically the time of flight, you can also have attenuation or loss of power in the signal as it propagates, which is also going to be frequency dependent. And this is typically because of a phenomenon called a skin effect. So why does skin effect actually happen? I haven't really discussed why skin effect happens, but first let's talk about what skin effect is. So imagine you had a conductor. So here you have a conductor, which is the cross section of a signal line at three different frequencies. What happens is at lower frequencies, the current distribution across the cross section is going to be very uniform across the cross section. But as you increase the frequency, what happens is that the current tends to sort of crowd more and more towards the periphery of the conductor, and less amount of current is going to flow towards the center of the conductor. And when you go to very, very high frequencies, the current is going to almost flow near a certain skin of the conductor or near the perimeter of the conductor. And the inside of the conductor is going to be completely devoid of any current flow. And obviously now, because the current is being crowded essentially to the periphery of the conductor, with frequency, the effective area of cross section that the current takes is basically reducing with frequency, and therefore the resistance is also going to increase as the frequency increases. This depth, this approximate depth on the approximate so-called skin depth that the current actually flows through with frequency is usually given in terms of the resistivity of the conductor, the magnetic permeability, as well as the frequency, and is given by the formula square root of 2 resistivity over frequency omega times mu. And this skin depth essentially represents represents a distance over which the signal drops by about 1 over e. So imagine the signal imagine that the current at the periphery was, say, some value I naught. The current density at the periphery was, say, the value J naught. Then the current density, once you move a certain depth delta within the conductor, the current density is going to fall by J naught over E. So it's going to go to J naught over E. So that's the definition of skin depth. So now, what is the skin depth going to do? So as the frequency increases, the current is going to crowd towards the periphery of the conductor. So the current is only going to flow through a certain skin depth. And so what happens? The resistance is now going up with frequency. And therefore, we know, and if you look at what the resistance does is, if say you have this link which has some characteristic impedance Z naught, the resistance is the resistance per unit length of this transmission line. And so when you send this signal through one end of the transmission line, the signal is basically going to decay or decay in strength. So it's going to decay in amplitude as it's propagating along the Z direction. And this exponential, so the envelope of decay of the signal is going to be e power minus alpha z, where alpha is basically called as the attenuation constant, is directly proportional to 1 over the skin depth. So as the frequency increases, the skin depth is reducing, so the alpha is increasing, so the signal is going to decay more exponentially in amplitude as it's propagating along the link. And because delta is frequency dependent, this attenuation is also frequency dependent. And these are some more details about skin depth. You can pause the video and look at this more. So this is how, what is the general expression for skin depth and how skin depth basically changes with frequency. And these are things I already discussed, but these are more sort of data-centric explanation for what skin effect is. So what is going to be the net effect of this frequency-dependent dispersion, or basically the frequency-dependent time of flight of the signal, as well as this frequency-dependent attenuation of the signal? So again, I represent this pictorically here to improve your intuitive understanding of this. So imagine you had this basically this signal, and these dash lines represent the locations where you sample the signal. So this is the 101011, and this signal can obviously, because of Fourier series, can be decomposed into its Fourier components, having a fundamental component and higher order components. And these are things we already talked about. So, and because the digital signals are going to be very, very broadband, they're going to have very, very, even a 1 Gbps signal, which has a fundamental of 1 gigahertz, is going to have maybe 10 to 50 times the frequency components that propagate through the transmission line. So now each one of these frequency components is going to have a different propagation velocity, a different phase velocity, and therefore they're going to arrive at different times at the receiver. And not only that, they're going to have different values of alpha, which is the attenuation constant, along this transmission line as well. And therefore they're going to decay essentially by different amounts throughout the length of this transmission line. So finally at the receiver, what ends up happening is the different frequency components are going to be attenuated by different amounts and also going to be shifted in time by different amounts. So that now at the receiver side, when you put all these frequency components together and you recover the signal, the recovered signal is going to have a whole bunch of distortions, noise, and reduction in amplitude. So the attenuation, the frequency dependent attenuation, is now going to reduce the height of the eye at the receiver side, and the frequency dependent time of flight is now, or the propagation velocity is now going to basically reduce the eye width because of the jitter in the signal. So the net effect of this, basically the attenuation being a function of frequency, as well as the propagation velocity being a function of frequency, is going to have the net effect of closing the eye from which was found at the transmitter all the way to the receiver. And this can obviously change, cause issues in timing, as well as issues in basically bit errors. So it's going to create signal integrity issues. So now let's change gears and talk about the next important factor when it comes to signal integrity, which is EMI and EMC, also called as electromagnetic interference. So the fundamental cause of electromagnetic interference comes from Faraday's law of induction. So imagine you had a current carrying loop as shown here. So this is a loop of wire. And imagine I have a voltmeter connected here. And now imagine through this loop of wire, I have a magnetic field that is changing with time. So from Faraday's law, we know that this time-varying magnetic field through this conductor is going to create basically a time-varying flux that is cutting through the conductor. And hence this time-varying flux is going to induce basically a voltage as you go along the loop of this conductor, which is given by integral over this closed loop of the electric field dr. And obviously the magnetic flux is just going to be the surface integral of the magnetic flux density integrated over the area. So if you assume that this magnetic field B is changing harmonically, that is, it is harmonic in time and has a certain frequency omega, and if you substitute that in this equation, you will basically find that the voltage is directly proportional to omega. So the amount of voltage that is induced in the conductor because of the time-varying field is directly going to be proportional to the value of the frequency of the magnetic field. So now consider the following case where you have, remember the link, there's a transmitter connected to VDD and ground, and then it's sending a signal basically called as, which we're calling as Vs of t, that is traveling through this channel of characteristic impedance Z naught. And it's going finally to the receiver side, which is also connected to some VDD and ground. And remember that when you talk about links, any link, remember that the link is not just one line that is connecting it. There's always a return path because current has to flow in a loop, right? So, for example, the microstrip, the signal line is the rectangular signal line I showed earlier, and the return path is just the ground plane, right? So there is some signal line and there is some return path which is shown here, which has also has a characteristic impedance Z naught. And so now what happens is now what you end up having is you basically end up having this big loop of wire that is just sitting there, which is the link itself. And now imagine you have other things near it. So imagine you had some other link nearby it that is basically creating its own time varying magnetic field because obviously the link is switching. So it's going to cause a switching current and therefore a switching or a time varying magnetic field. Imagine you had other things that are radiating nearby, such as, for example, a phone or an antenna or something like that. This magnetic field, this time varying magnetic field from these various sources is now going to cross this loop. And because of Faraday's law of induction, these time varying magnetic fields through this loop is now going to induce a voltage in the loop, which is going to turn up as noise in the signal that is propagating. So now what ends up happening is this Vs of t that is propagating is going to be added with a certain noise signal, V noise of t, so that at the receiver side, the signal you get is going to be just the signal at the source with some phase shift, which depends on the length of the transmission line, added to this noise, V noise of t, which is the EMI, the electromagnetic interference noise, which is added on top of the signal that was sent. So, and obviously, because I talked earlier that the voltage that is induced, this kind of Faraday induction voltage, is going to be proportional to the frequency. Therefore, the higher frequency electromagnetic interference, so the higher frequency radiation from nearby objects or nearby transmission lines is going to have a much greater impact on the noise voltage that is induced in the loop. So generally, this kind of EMI noise tends to be very high frequency because the higher frequency time varying B fields nearby is going to induce a higher noise voltage in this loop of wire. And here it is often very useful when you talk about EMI to describe something called as the SNR or the signal to noise ratio, which is simply defined as the signal power at the receiver over the noise power. And if you calculate this based on the expression I'd written earlier for the signal received at the receiver side, it's just going to be the signal power is just going to be Vs of t e power minus alpha L, and square because it's a power. So power is the voltage square. So it's going to be the square of this voltage over the noise voltage, just V noise square. So this is going to be the expression for the signal to noise ratio. So you see clearly here that it's going to have this exponential minus 2 alpha L term, which means that the signal to noise ratio is going to fall exponentially dependent on the attenuation in the link as a function of the length of the link. So that's why long links are not good because long links are always going to have some loss in them, and therefore they're always going to have some attenuation constant. And so if the links are made too long, the signal to noise ratio is going to be so small that now the noise signal is going to be very comparable to the actual signal you send, so that at the receiver side, the receiver can no longer tell if what it's sampling is going to be the signal or going to be the noise, and this is going to lead to bit errors. So you always want to keep the signal to noise ratio as high as possible by either by reducing the length of the link or by reducing the noise voltage by basically shielding, which we will see later, shielding the link from all these different radiating sources and so on. And sometimes if it's not possible for you to do any of this, you can also add things like repeaters that boost the strength of the signal along the transmission line. So that ends up also increasing the signal to noise ratio. So this is all I've already described, why a high SNR is actually good. And what is the issues with the low SNR? So what is the issue? So you have, say you send a bit stream, a bunch of zeros and ones here. So when the signal propagates, the presence of nearby radiating sources or transmission lines is going to induce this Faraday voltage here, which is going to show up as a noise signal. and therefore at the output, you're going to have a very noisy signal. So the signal to noise ratio of this signal here is very low, then the noise signal, as I said earlier, is going to be quite large compared to the signal. The noise voltage is going to be quite comparable to the signal voltage, and this can lead to bit errors during sampling as well as timing issues. So, what are some ways to mitigate this electromagnetic interference as well as noise? So, one obvious way is to shielding, right? So, imagine. So, remember that the main source of this noise is just nearby radiating sources next to the link. So, one way is to just completely put a wall around it and prevent the signal from coupling into this transmission line. So if I put a metal case, and it doesn't really matter whether the metal case is a continuous metal or a mesh, it will behave the same way. And if you have this metal mesh or a metal cage present along the link, then any nearby noise signal is just going to reflect off this metal cage and won't end up coupling into this link. And this is another version of this typically already described earlier when I talked about the PCBs, where you put this sort of ground plane or voltage plane to separate layers of metal from each other. And what these ground and metal planes do is they also shield the electromagnetic radiation from one layer of metal to the other layer of metal. And so this also prevents the noise from coupling. The second, and this you can see here, this is a actual picture of a PCB where you have this EMI shielding on it, which is, as I described earlier, is just a metal cage that is put on top of their links. The second one is the use of dampers. Name suggests the dampers just dampens the noise signal. It doesn't prevent the coupling, but it just dampens the noise signal. So imagine you had this link here, which is a transmission line. And what you can do is you can actually encase a ferrite core around this transmission line. And here's an example of what that looks like. You would have seen this commonly with the communication cables. They have this kind of a circular cylinder around it. Inside the cylinder, there's actually a ferrite core that kind of wraps around this conductor. And what happens is, you remember, imagine that the signal that's going to be traveling along this transmission line is going to be the signal that I sent, which is Vs of t, added to some noise signal induced by nearby radiating sources. And what happens is this noise signal, because this noise signal or noise voltage signal is going to induce a noise current in the transmission line, and this noise current is basically creating its own magnetic field, which is varying with time. And this magnetic field that is passing through this ferrite core or linking to the ferrite core can induce, because of Faraday's law of induction, induce eddy currents in this ferrite core. And these eddy currents basically would cause power dissipation and will therefore cause an increased attenuation of these noise signals. So remember that the eddy currents, if you go from basic electromagnetism, the amount of eddy currents that is induced inside a magnetic core is proportional to the frequency. And the eddy current loss is actually proportional to the square of the frequency. And therefore, by having this ferrite core as a frequency of the noise signals, which have a very high frequency component, they're going to have a very large attenuation in the ferrite core, and therefore the ferrite core essentially ends up dampening these high frequency noises, so that at the end of this particular length of the ferrite core, most of the noise signals have been attenuated and the signal strength has been reduced significantly, so that at the output the SNR is now improved. And this is another way that you can reduce the effects of EMI on signal integrity. And the last one is, sometimes it may be very difficult to kind of remove this noise, especially if and even if you remove the noise, there could still be some amount of noise. And if the signal strength is very low, then the SNR of the signal is quite low, and it becomes very difficult to distinguish the signal from the noise, even if you do all these strategies of shielding and damping, right? And so sometimes you need to do things like error correction, wherein in the data that you send, you add redundancies and error correction bits. And in the software domain, you can basically, there are software ways to kind of recover the data, even though the data has been corrupted by the noise signal. So these are some 3 mitigation strategies to deal with electromagnetic interference. So based on everything we discussed in these series of lectures, let us now look at how in a real system, like in a real PCB board, for various frequencies, how they actually implement everything we learned. So if you look at this is a typical high-speed digital board, and you see here how you can see here You can have a look at the self and try to identify various things we discussed in this entire presentation. You can see here how whenever you have a bend in the line, you have basically you don't have a sudden 90-degree bend, but it's a 45-degree bend, and that improves reduces the reflections. And also you notice that some of the links, so if you have like three links here, they have a whole bunch of serpentines added to them. And the reason they add these serpentines is you want all these signals, because remember these are like all parallel signals, and all these signals are synchronous, so you want all these signals from the transmitter to receive at the same time at the receiver side. So if each signal line was a different length, then each one of these signals will be received at a different time at the receiver. So this serpentine, what it does is it basically matches the electrical lengths of all three links, so that all three links have the same time of flight, so that the signals sent simultaneously from one side will reach simultaneously at the other side. And so these are the main kind of things that you can like kind of immediately see on this high-speed PCB. If you go to even higher frequencies, on the right, you see a PCB that is designed for much higher frequencies, up to 50 gigahertz. In this case, you end up never having these kind of 45-degree bends, and you actually end up using the adiabatic bends I talked about earlier, because even these 45-degree bends are not good enough at these high frequencies because they induce reflections, they induce basically the exciting of higher order modes and so on. So here you see a high frequency 50 gigahertz RF package where you have basically these adiabatic metal interconnects here, which are microstrips. And then there's a high frequency wire bond, which is typically a ribbon type wire bond that connects to these transmission lines. And these transmission lines are, as you can see here, are bent adiabatically. And finally, the signal is basically fanned in, and then there's again a ribbon bond here, and then sent all the way to this chip. And this is for a much higher frequency application. So you see how, depending on the application, depending on the frequency, the kinds of designs, the kinds of mitigation strategies that you use for signal integrity can be very, very different. So let's talk now a little bit about a case study. Everything we learned in these set of lectures on signal integrity to how to design fan out wires or fan in wires on a ceramic PCB for a photonics package. For example, a silicon photonic integrated circuit to SMAs at a frequency of about 50 gigahertz. So this was actually a design I had done around a couple of years back at IIT Madras in India, and I thought I would include it here because it kind of uses many of the concepts that was discussed in the signal integrity classes. So the main kind of package. So this is the design of the full RF package that you can see here. So here, let me describe some of the components. So this pink thing here is basically a photonic integrated circuit, and this PIC has a bunch of photonic components on it. For example, it has a photonic modulator, and the optical signal to this photonic modulator is coupled using these fiber arrays. So these are actually quasi-planar couplers, which are QPC fiber array couplers that are kind of attached to this PIC. And then you also need to, and these basically send a laser signal, which acts as basically the oscillator, which basically acts as the oscillator frequency for this modulator. And then that oscillator frequency is mixed with the actual signal frequency, which is sent as an RF signal through this RF PCB. So, so the functionality is basically you have this modulator, you're sending basically the oscillator frequency through a laser, and the actual signal that has to be modulated is sent through this RF PCB to the PIC. And once the signal is modulated in the optical domain, the optical signal, modulated signal, is then sent out through the second QPC. This other DC PCB basically has a bunch of basically DC control lines that is used, which is beyond the scope of this lecture, but it is actually used for temperature control on the PIC for the operation of the photonic modulator. So how did I go about designing such a link? So remember here, imagine here that there's the SMA connector. So the SMA connector has a very large pitch. The pitch can be around hundreds of micron. And then this pitch has to be kind of fanned in all the way to the die, where the die side pad pitches are around, say, around 80 microns. So it has to go all the way from hundreds of microns to 80 microns. So you need to take the RF electromagnetic signal that comes in from the SMA here, and this RF electromagnetic signal has to be fanned in all the way till here, making sure that each one of these links have the same time of flight, and also each one of these links are perfectly matched to 50 ohms so that you can minimize the signal reflections and ensure best signal integrity. So the way I designed this is all of these transmission lines were based on coplanar waveguide without a ground connection. So they were a CPW kind of structure. And for the CPW kind of structure, you can have this is the typical analytic expression for the effective dielectric constant and the characteristic impedance of this transmission line, which was already talked about in lecture 1. And so, based on the dimensions at the SMA here, as well as the pads on the PIC, I designed coplanar waveguides near the PIC over here, as well as near the SMA over here, based on these equations. And then initially, I just designed a linear taper that goes from the pitch on the SMA to the pitch on the pads of the die. So here's a typical design of this linear taper. This taper was done in an adiabatic way. And as you see here, the length of this taper, it's a linear taper, and the tapering happens linearly over a length of around 10 lambdas. And you see here how the signal is basically being compressed as it goes from the SMA side all the way to the die pad side. And you can see this is the return loss as well as this is the insertion loss. You see that the return loss is throughout the frequency range of interest. We particularly care about 50 gigahertz, but this thing can operate up to 50 gigahertz. So throughout the frequency range of interest, the return loss or the S11 is less than minus 20 dB, which means that this link is basically perfectly matched. And also, you see the insertion loss is also very close to 0 dB. There's some decrease in the insertion loss with frequency because of the frequency dependent loss in the measure. And if you look at the S11, which is the return loss, can also be plotted on the Smith chart. And you see here that initially at low frequencies, it has some basically, it has a impedance which could be different from 50 ohms. But as the frequency is increasing, you see how it goes and settles at 50 ohm impedance, because this link was designed at 50 gigahertz, and therefore at lower frequencies is not perfectly matched. But once you go towards the higher frequencies, towards the 50 gigahertz where it was designed, you see that it is more perfectly matched. If you see here also, you notice that this return loss is not very uniform. It has these kind of ups and downs in it, which are very characteristic of having some kind of reflections. And the reason why these kind of reflections are occurring is because this entire transmission line is not perfectly matched to 50 ohms. There is some mismatch. So this kind of humps is occurring because there is some signal that is reflecting from either side of this transmission line. Because in the simulation setup, the extremities of this transmission line are set to exactly 50 ohm matching. So there's some reflections is basically creating this sort of periodicity in the return loss. Now, as I described earlier, so not only does the signal has to taper all the way down here, it also has several bends because you have to kind of fan in the signal. And so how did I design so I kind of, when I went through this entire design of this RF link, I kind of split it into several individual designs that I kind of put together. So first I started with designing just the 50 ohm impedance transmission line at the SMA side and the pad side. Then I designed a linear taper, but it was a straight taper. Then I look at the effects of bends, and then I combine everything together to create a fan-in that basically has both a taper along with also a bend. So now I basically analyzed a situation where I studied the effects of different bending angles, so different basically radius of bending on the insertion loss. So obviously, from our earlier description, you see there's some input power sent from 1, and then you see as a function of the bending angle, what is the output power that is received, and then you basically find the insertion loss by taking the 10 log to the base 10 of the output power over the input power, right? And that is the insertion loss. So what you see is that as the bending angle, the bending radius, so this is the bending radius. So as the bending radius is increasing, or the bending is becoming more and more gradual, what ends up happening is the bending becomes more adiabatic, and this adiabatic bending basically reduces the signals, reduces the reflections of the signals as they go from one side to the other. Each side of this transmission line is basically already designed to be exactly 50 ohms. So you see here how as I mentioned, this is the S51. Sorry. Yeah. So you can see here how the S51, which is basically and because this is terminal 5 and this is terminal 1, S51 is the insertion loss in dB. And you can see how the insertion loss is changing with frequency for different radius of bending. And you see that for the radius of bending R3, which is much larger, you see that the insertion loss is much closer to 0 dB, which means that it is much better match for the frequency range of interest up to 50 gigahertz. But you see that for the cases where the radius of curvature is much smaller or the bend is much sharper, you notice that the fall in the insertion loss is much more rapid with frequency. So this is not good, right? And now if you look at the so this is qualitatively, and quantitatively when the simulation was done, it was found that the value of this R3 was around 20 millimeters. So if throughout the link, so throughout the fan-in of the link, if I make sure that at any location, the radius of curvature or the bending radius of this link is greater than 20 millimeter throughout the length of the link, going from the SMA to the pads on the PIC, I can basically ensure that I can maximize the insertion loss, or I can basically minimize the return loss, right? And therefore, it is better matched. So that's precisely what I did here. So this was the completed design, and this completed design had both the linear taper that I designed earlier, as well as the fact that no matter at any point along this fan in, the radius of curvature does not go less than 20 millimeters. So the radius of curvature is always greater than 20 millimeter at any point on this link. And basically, you have 4 links because you have 4 signal inputs that is being fanned in to the die side. And this is the basically the structure simulated in HFSS. And now here is the results. So you see this is the 4 inputs where the 4 SMAs are connected, and these are the 4 outputs where the dies are present, the die pads are present. So this is labeled as port 1, 2, 3, and 4, and 5, 6, 7, and 8. And therefore, S11, which represents the return loss of port 1, as you can see here, is at 50 gigahertz, is perfectly matched to 50 ohms. And similarly for the second link, the third link, and the fourth link. And here I've basically plotted the same S11 value, but in a rectangular plot. And you see that the return loss is basically around minus 30 dB over the entire frequency range of interest. And at 50 gigahertz, it's less than minus 30 dB, which is what I designed it for. And similarly here, you see the insertion loss is good. And what about the crosstalks, right? So if you notice this, this field animation, you see that the signal is sent from port 1, and the signal is basically both tapering as well as fanning in and bending as it goes from the SMA all the way to the pads. But you notice that some of the signal is also seems to be going through port 2 and port 3. And remember, for the simulation, port 2, 3, 4, 5, 6, 7, 8 are assumed to be matched to 50 ohms, and only the port 1 is being excited. So the signal that is going back to port 2 and port 3 is actually the signal that is coupling from port 1 in this region where they are coming very close to each other, and then it is propagating, it is kind of reflecting at this port 6 and then propagating back towards port 2. So this is actually the cross coupling that is happening between the 2 links, because they're coming very close to each other, and therefore the capacitive effect of coupling between the 2 links is causing some energy to jump from from the link 1 to link 2. So this is the link 1 would basically be the aggressor, and link 2 would be the victim, right? And so that's what I have basically described here. This is the kind of the schematic of what I'm doing here. I have basically these 4 fan-in links that I've designed, and through port 1, I've connected the transmitter that is sending the signal. and port 5, 6, 7, 8, 2, 3, 4, 2, 3, and 4 are assumed to be perfectly matched. And what the simulation does is it assumes that in each one of these ports are connected to an infinite transmission line of characteristic impedance Z naught, so that these lines are basically completely matched to 50 ohms, and there cannot be any reflections. And so these are matched to 50 ohms. So the power P1 that goes here, some amount of it is obviously transmitted to Z naught. And since if this is perfectly matched with Z naught, then all the power would go. But you notice that some amount of the power also couples to basically to the second line, which is because of the crosstalk. And this creates a power P61, which is basically the power that is going into terminal 6 because of the excitation in 1. And similarly, you have P21, which is the power going to 2 over the power that was sent from 1. So from our earlier definitions of crosstalk, the 10 log to the base 10 of 10 log to the base 10 of P51 over P1 is just going to be the insertion loss, because that is the signal that is being sent into port 5 because of signals sent through port 1, and that's the insertion loss. The far end crosstalk is going to be 10 log to the base 10 of the power going through 6 due to the power in 1, and the near end crosstalk is going to be 10 log to the base 10 of power in 2 because of the signal that is sent in 1. And this is just based on this is just kind of refreshing what I talked earlier on about the far end crosstalk and near end crosstalk in the crosstalk section of this presentation. And here you see the plot of the crosstalk value in dB versus frequency. And here you see I basically plotted S61 and look particularly at S61 as well as, Oh, yeah, sorry. This is just the far end crosstalk. It's not the near end crosstalk. So look at, for example, S61, which is basically the far end crosstalk. And what you notice is that the far end crosstalk at lower frequencies is less than minus 60 dB. So it's a very, very small value. And as the frequency is increasing, you see how the crosstalk is also kind of increasing. And it's becoming more and more closer to minus 50 dB at around the frequency of 50 gigahertz. And this is basically the effect I was talking about, that as the frequency is increasing, this kind of cross-coupling capacitance, the parasitic capacitance between the links, is also increasing. And therefore, there's going to be more cross-coupling. And that is the reason why more amount of power is getting cross-coupled from the aggressor to the victim as the frequency is increasing. But in this design, it's still less than minus 50 dB, so it's pretty good for this broadband 50 gigahertz, for this 50 gigahertz design. Okay, and that concludes the lectures on signal integrity. Thanks for your attention.